Mm. Hello. Hello, hello. Um, okay. Y'all okay? Ready? Okay, we start. Okay. Sorry, guys. Okay. But anyways, yeah. So today I'll just be covering like PYP because if I cover like everything, right, there won't be enough time. There's a lot of things lah, basically. Yeah. So I'm going to just cover like what's it called? The thinking like what like when you yeah. As in like when you see like the question uh like what they expect you to think lah, basically. Okay. You all can hear me, right? I'm not wearing the mic lah, or else it will, yeah, it will, what? What's the word? It's the double. Yeah, echo. Yeah, that's the word. Okay, and yeah, Zoom people can also hear me, right? Yeah.
Yes, yes.
Okay, nice. Thanks. Okay, then we just start like. Okay, so for first question, right? It's always about the site investigation. Okay, so um I would like to think of it as like you're being the engineer, like you're on site. What do you want to do? Usually it's like that. Okay, that's the important thing. Second important thing is to know the symbols. Okay, because there's a lot of correlation in the first question. Like from SPT, how do you get this? From CPT, how do you get this? So you need to know the symbols. Okay, what the meaning of the symbols. But anyways, for question A, for example, briefly describe the main task of site investigation. For example, so this one is pretty straightforward. So imagine you're being on site, you want to know the condition of the soil. So there are in total 7 steps. It's here. Is yeah. So I'll just keep that. So basically, right? Again, you do desk study first. You check the past documents, right? Then after you see the past documents, you cross check it with the actual site. So you go to the site visit. Okay. So check the past documents. So desk study. Then go to the site visit. Then you go. Then you go to plan the SI task. Okay, so you plan the SI task. So based on the data collection, based on your site visit, okay, I want to put a borehole there, borehole here. So you start planning your SI, site investigation. Okay, after planning your SI, what do you do? Then you start the in-situ test. Okay, you start drilling basically. So this is what we call the subsurface exploration. Okay. Then after you get the in-situ test, sometimes you want to take it to the lab, right? So you have the soil sampling and lab testing. So soil sampling and lab test. Then after you get the lab test, what do you need to know? You need to know the water conditions, right? Because it's not all about the soil. So you go to that one, groundwater exploration. So groundwater table exploration and monitoring. So now you have the soil information, you have the water information. So in the end, you just need to combine them together. So synthesis of data. So synthesis of data. Yeah, so these 7 steps are like connected to each other. So you should know this. Okay. So for the second one, they ask you about the difference between disturbed and undisturbed. So this is like quiz one. Again, you have a block of soil, right? Imagine it as a piece of cake. Okay. So if you if you grab the cake with your hand, right, the cake will crumble. If the cake crumbles, then a lot of things will change. like the volume of the soil will change, and of course the strength is not there anymore. Okay, because the cake is not there anymore, it's crumbled, right? So that's what disturbed soil is. So disturbed is basically crumbled already. You can think of it that way. Undisturbed, it keeps the soil structure. So it has not crumbled yet. So for disturbed samples, you can only take what is it? Okay, but anyways, for undisturbed samples, that's where the soil strength comes in. Okay, you can only measure soil strength if the soil is not destroyed. If the soil is disturbed, it means like crumbled, right? How can you take the strength? So that's the logic behind it. That's why anything to do with strength like goes to the undisturbed. Okay. Well, for disturbed, here you can only take the density and density, water content, and Atterberg limits. Okay, so density, water content, and Atterberg limits. Atterberg limits is the LLPLPI. It's the liquid limit, plastic limit. Yeah, it's this one. Oh, sorry, gamma is undisturbed. Sorry, gamma is undisturbed. Yeah, you can only take water content and Atterberg limits. Yeah, anything to do with strength, right? So consolidation, UU, CU, CD. This one is, the C prime and the phi prime, your friction angle, right? And CU, that's all under the triaxial test. That's not anything to do with strength, right? It's always undisturbed. Okay. Okay, strength and consolidation, something like this. Anything to do with strength and consolidation is undisturbed. And undisturbed also, you can use it for water content, and you can also use this for it because undisturbed is like the best soil sample. Okay, but we cannot get it all the time. It's very hard to get the undisturbed ones. Okay. Yeah, this one are just some guidelines. So yeah, water content, Atterberg limits, compaction test. I think you can also do disturb. I think, yeah. But the rest, right? The rest is particle size also you can do undisturbed also. Yeah. Sorry, you can do disturb also. Particle size. Because particle size, right? It doesn't matter whether the soil has crumbled or not. This is the same material. If there's the same amount of fines, there's the same amount of sand. That's why you can put particle size under disturbed. Okay. Yeah, then consolidation, this one are strength. So all of these are undisturbed. It's the best soil sample. Okay. Okay, now let's go to part 3. Now, this is what I meant by knowing the symbols. Okay, at the back of the in the back of the paper, they will always give you something like this. They will always give you like some correlation, what's it called, formula. Okay, this one you cannot derive. They will just give it. Okay, your task is just to use it properly. Okay, so if you notice, there are some symbols. There's QC. There's the sigma prime VO. Yeah, that's it, right? Yeah. So QC and sigma VO are in kilopascals, for example. Okay. So yeah, just take note of these first. Let's go back to the questions. Okay. So you have a CPD test. Okay. Okay. So they give you QC. So QC is the tip resistance. Okay, which is 8.1 megapascals. So what that means, right? So this is your cone. Your cone will have some resistance at the tip. That's what we call QC. Okay, so for every CPD test, there's always QC and FS. FS is the side friction. Okay, but that one you can refer to, yeah. Okay, then we give you the unit weight of soils above and below the ground table. They give you the water table, right? So now you need to know the relative density and effective peak friction. Okay, so again, it's based on these two formulas. So it's literally just plug in, right? So you have the relative density ID, you have the friction angle, okay, phi prime. So in that case, let's just copy the formula. So ID, relative density, is D plus E log QC divided by sigma V prime 0.5. Okay, so QC, we are given QC, so we know what QC is. Now what's this? So how to read this, right? Sigma prime means effective stress, right? Effective stress. V means vertical. Okay, V means vertical. 0 means initial. Actually, that's what it means. So initial vertical effective stress. Now you know. So it's actually initial vertical effective stress. Okay, because sometimes we have like some consolidation and everything, but usually not tested. Right? So yeah, so this one initial. This one means vertical. This one means effective stress. Okay. So what do they give us? They give us the measurement is measured at 12.2 meters below ground, right? So if this is your ground, they measure it 12.2 meters. So here, okay, they give us the water table is 2.8 below. So it's here. Okay. So basically, sigma V 0 prime, right, is the effective stress at this point. Okay, so how do we calculate effective stress? We just take the weight above and minus the water, right? So in that case, they give us the gamma here is 16.2, right? The gamma here is 17.2. Okay, so the effective stress, initial vertical effective stress is 16.2 times 2.8, right? That's the weight of the soil here. Okay. Plus, now we need to use the buoyant unit weight, the effective unit weight, because we're finding effective stress, right? So in here, it's 17.2 minus 10. Minus 10 is the gamma water. Okay, because we're taking effective stress. So we need to minus off the water. If it's saturated, the top one is dry. So that's why we don't need to minus. Okay, multiplied by this depth. So it's 12.2 minus 2.8. So 12.2 minus 2.8, you'll get 9.4. I'll label this like this. 9.4 meters. By the way, the workings are inside CE website. Yeah, so here I'm just explaining, but if you want to see the full working, just go to CE website. Yeah. But anyways, so this one multiplied by 9.4, right? So you will get what? 67.68. This one? Oh, this one is excessive. What's the total? What's the total? 113.04. This one in kilopascals, right? Yeah. So now that we have this, it's just plugging in the formula. So legit is you need to be aware what the symbols mean. It's all about that, yeah. Okay. Why wastewater? Okay. So in this case, I think D and E is given, right? Yeah, D and E is given as negative 1.21 and something, right? So negative 1.21 plus 0.584 log. So QC is given as 8.1 megapascals. But look at here, it's kilopascals, right? So we need to change the units. Okay, so 8.1 times 1000 divided by 113.04. Okay. Yeah, let me move this around. Okay. So just find ID. Okay. Then for friction angle is the same thing, just a different formula. So I'll just skip it. Okay. But you get the idea. So you just need to find what the symbols mean. Okay. Then plug in. So that's number one done. It's very fast, actually. It's very fast. But it really requires your understanding. That's the hard part of number one. Okay. So any questions so far? Number one? I remember I finished it exactly the timing actually. Yeah. It's barely finished. I think it's because of it's because of this. It's because of this. It's because of this. It's the settlement. We'll go there now. Okay. Okay, anyways. So 2A is another theory question. So how partial factors are applied to actions, solve property, and resistance. Okay, so in a nutshell, your actions should be less than your resistance, correct? Your resistance must be bigger than your actions, okay, or else the soil will fail. That's the general idea. So how do you present it? Wait, let me check the strat, please. Oh, okay. Okay. Anyway, okay. So how do you present your answer, right? So your actions, you have your own partial factors, right? You multiply your actions. Okay, we want it to be more conservative. That's why we multiply the actions. So I forgot what symbol they use. I think it's Q. Okay, this one should be less than your resistance. So resistance, you divide your resistance by the partial factor. Okay, you divide your resistance by a partial factor because we want conservative, right? Then this resistance is actually a function of your materials. Okay, it's a function of your materials. So usually you put a bracket here. I think materials, they use the symbol X, yeah. So X divided by gamma X. Done. Okay, that's how you represent your answer. Okay. Yeah, so action is the Q. Yeah, action is Q. Soil property is this one, and resistance is your R. Okay. Let's go to the next one. So for the question 2, it's always shallow foundations. Okay, I'll just give you a recap on what's in shallow foundations first. So okay. Yeah, that's why I knew it. Here. I think I'll upload this. Why not? Okay. I'll accept donations. This one I'll just give because you won't bring this in the final exam anyways. This one. Okay, so let's go to shallow foundations. By the way, okay, maybe a recap on question 1 as well. Why not? So there's the overall picture, like the one just now, the 7 steps of SI. Then there's the sampling part. There's a few ways to do sampling. There's a few ways to do boreholes. Okay. There's in-situ test, so SPT. Okay, SPT, you have all the correlations. You don't need to memorize. They will give you the correlations. You just need to know how to use. Okay, again, you need to know the symbols only. So SPT, CPT, yeah, CPT, you have QC and FS, tip resistance and shearing resistance. Again, they will give you the formulas. You just need to know how to work it out. Okay. Then what else? Field drain, FVT. So again, they will give you the formulas. And that's it. So SPT, CPT, FVT. So these are the 3 soil tests. Then the rest is like soil sampling and boreholes. Yeah. So this. Then for shallow foundations, okay, first there's bearing capacity. So basically, if you put the shallow foundation on the soil, right? If you put some load, will the soil break or not? That's what bearing capacity is. Okay. Punching shear, general shear, this one is covered in your RC. So yeah, it's not in this course. Okay. So for ULS, I think it's only bearing capacity in foundation. Okay. We have drain and undrained cases. Yeah, so this is the undrained case, and there's the drain case. Okay, so bearing capacity is just undrained and drainer. Then after that is settlements. So actually just two for shallow foundations, bearing capacity and settlements. Okay. Yeah, no side friction because that's pile. Yeah. Then settlements, there are four things that you need to study. The first one is your elastic settlements or immediate settlements. So if you put the foundation down, the soil will immediately settle. Yeah, so that's one. Two is consolidation. This one is covered in your soil max, I think. So it's quite similar. We're going to do this soon. Then you have SPT and CPT. So four things, right? For shallow foundations. Okay, but okay, again, let's go back. So now you're given a square footing, depth 0.5. Then they give you the characteristic total unit weight. Again, characteristic means unfactored. This means unfactored. Okay, so now they are okay, now they have a loading, Raman action, then variable action. Now find the bearing capacity of the footing based on DA1C2. Okay, so based on DA1C2. I'll make a new page. Okay, let me scroll to the relevant. There. Okay, first things first, we need to check, is it drained or undrained, right? So we check, it's clay. So this is undrained analysis, undrained, okay? Second one, okay, so for bearing capacity formula, I'm too lazy to scroll. But you need SC, NC, CU, and sigma Q. Okay, so QF, so this is your bearing capacity. Okay, QF means bearing capacity, yeah. F means foundation, I think. Yeah, that's the small f. But anyways, SC, NC, CU plus sigma Q. So these two, SC and NC, are factors. S means shape. Okay, so SC means the shape factor, NC means the bearing capacity factor. CU is the shear strength. Sigma Q, again, this one is the total stress. Okay, Q means at the foundation. Okay. Okay, so anyways, the foundation is, the bottom of the foundation is here, correct? So sigma Q means the pressure here at this level. So that's what sigma Q is. Oh, bottom. Okay. Okay. Somebody asked just now if there's a foundation this way, right? The logic is like your foundation will transmit the load where. Okay. If you have a foundation here, then it will transmit the load to clay 2. So you will use the CU of clay 2. But in this case, our foundation is transmitting the load at clay 1. So later, if you have a CU, you will use the CU of clay 1. So that's the logic behind. Okay. So let's find this one by one. This one is DA1C1. Oh, DA1DC2, DA1C2. Okay, so for DA1C2, okay, so we need to find the design material properties for DA1C2. Okay, so for DA1C2, so let's start with CU first. So CU is, so CU design is 35 divided by 1.4. Then gamma stays the same. Yeah, nothing else for this information. Okay, so it's just 35 divided by 1.40, so that's 25. Okay, you can refer to the table behind, but yeah. So that's the A1C2. Then for the A1C2, I think the variable action is multiplied by 1.3. You can check, okay? So, okay, let's list down the parameters first. Okay, they give GK to be 1110, right? 1110 kilonewtons. QK to be 30 kilonewtons. Okay, check the ULS bearing capacity. I'm quite jumping around actually. Okay, but anyways, again to check you need the actions and resistance, right? Let's do the resistance first, why not? Yeah, and actually you can do the actions first, but same thing. So let's do the resistance first. So SC, I think they give you the formula. SC is 1 plus 0.2 B over L, right? So B over L is 1 by 1, right? Yeah, B is 1, L is 1. So 1 plus 0.2, that's 1.2. Okay, this one is B is 1, L is 1. It's a square footing. Yeah. Then they give you NC, right? So NC is 2 plus pi. Some of you asked in the lecture notes, the NC, the formula is different, but that's based on assumptions. So just follow what they give you. If they give you 2 plus pi, use 2 plus pi. Okay, I think let me check I don't know why they give 2 lah. Where is it? Ah, yeah, this one. They give you NC equals 2 plus pi times somethings, right? So no, it's also under. Oh, oh, okay. Then no wonder. It's fine lah. But anyways, we use this value. Okay. Then sigma q is the total stress at the foundation level, right? So sigma q is 18 times 0.5, correct? So it's 9 kilo pascals. Therefore, QF is so SC 1.2 times 2 plus pi times CU, which is 25 plus 9. So that will give you 163. So that's your resistance. Now let's find the action. I think action is even easier. So action, I'll use the symbol W. I think sometimes they use N, like small n, but same thing. So 1.35. Sorry, this is the A1C2, right? No need, I remember. The A1C2, right? Your permanent action is 1. So it's only 110 plus your footing weight. So that's 24 times 1 times 1 times 0.5 plus 1.3 times the variable action, which is 30. Okay, I'm referring to this table behind. There. I'm referring to this. So multiply by 1, multiply by 1.3. Okay. So let's go back. So in this case, your action is 161, right? Kilo pascals. Oh, this one is barely okay. So something like this. Okay. Yeah. I might need to check the values. Why is it very close? uh, yeah, I can open my own solution and hmm, okay. Correct. The values are correct. Yeah. Oh, they use RD and QD. Oh yeah, those are the symbols. Okay. Oh, I forgot to times the area. Sorry if I say. Okay. Yeah. Okay, this is still in kilopascal. Sorry. This one is kilopascals, right? So your resistance, you just need to multiply by the area. So 1 times 1, right? So still 163.2 kilonewtons. This one is kilonewtons already. See? This one is in kilonewtons. Okay. So this one action is QD, right? So QD less than RD, so it's okay. So that's the steps now. Okay, action and resistance. Always 60. Okay, now let's go to the next one. Okay, so now they ask us to estimate the consolidation settlement of the footing using Coduto's recommended number and thickness of soil layers. Stress increase use 2.1, 2 by 1. Okay, then no correction for three-dimensional effects. So plane strain. Okay, so plane strain condition. It means 2D lah, basically. Okay, so again, there are 4 cases, right? Immediate settlement, consolidation settlement, SPT, and CPT. So we're doing the consolidation one. I think the idea, right? I think for immediate and consolidation, they always see it in layers. Yeah, I think you can think of it that way. Okay. Because we can, of course, we can consider the whole chunk as one big chunk to consolidate directly, but usually they split it to like small chunks. Okay. So in this case, what's the conductor's recommendation number on thickness, right? This one, for some reason, they never give. You need to memorize it. I'm quite surprised. It's where is it? I remember it's here. Yeah, sorry. Yeah. Here. So recommended layers for manual competition of SC. Okay, so we're doing square footing, right? So the layers are 4 layers, B over 2, B over 2, B and B. Okay. Um. Okay, I'll show first. Okay, I'll show first. Okay. So the recommended one is B over 2, B over 2, B and B. Okay, so B is 1. So B is 1 meters. So half, right? So B over 2 is half. Okay, so now we can just start drawing the layers. Okay, we're putting the weight at that red line, right? That's where the weight goes. Okay. So only the soil below that weight will consolidate. Okay, so B over 2. Okay, again, the layers are B over 2, B over 2, and B and B. So we do 0.5 first. So the thickness of this is 0.5. The second one is also 0.5. So this layer 1, layer 2, layer 3 is B, right? So that's 1. Wait, so this one is how much? 2.5. Let me There is 4. Okay, so we have 4 layers now. If you calculate the depth, right, it's 0.5 plus 1 plus 1 plus 2, so that's 3.5, right? So that's actually exactly at the bottom. It's exactly at the border. So basically, what we're saying is we're only calculating the consolidation of clay 1. Okay, clay 2, it's outside the range of the zone of influence already. Okay, because the recommendation is this one: B/2, B/2, B and B. Okay. So now what to do next? So for each layer, you take the middle of the layer. Okay, because that's like the quote unquote average of the layer, you can say. Okay, and in fact, the why we do layers, right, is because we want greater accuracy. Because if we take the whole layer, then we're averaging the what's it called? Averaging the very high layer, and we don't want that. This one is CPT. Consolidation is this one. They only give this, okay. So they only give this, right? Okay. So before we even start, right? Let's do let's analyze what we need first. Okay. So they give um OED. OED is oedometer. Yeah. It's to measure consolidation settlement. So it's H divided by 1 plus EO CR log this something like okay. Okay. So let's analyze first, yeah. So what we need is first one is H. So H is your layer depth. Okay, so initial layer depth is this much. Then we're consolidating, right? So H is the original layer depth. Okay. So in this case, this H, H1, H2, H3, and H4. Okay. So H is the initial depth. Okay. E0 is the void ratio, right? So it's a given. Okay, it's a given here. E0. Okay. Now this part, if you notice there's CR and CC. Okay. This one is CC log sigma P divided sigma final sigma P, something like this. Okay. So if you remember consolidation, the graph looks like this. Looks like this. Okay. Do you remember actually? Just curious. This one is the CR and CC. Then yeah, it's the recompression curve. Okay, so there's the Pearson compression curve. There's the recompression curve. Okay, it can be represented like this. Okay, so something like this. Okay, it's basically saying if your soil is overly consolidated or OC soil, right? Then your starting point is somewhere here. Okay, that's your settlement line. Okay. This one is I think this one is stress. This one is settlement. I think. Okay. So if you load it a bit, right, it will settle this much. But if you load it even more, then you have two parts of the curve. Okay. So the first part is this one, CR, because this is where the recompression happening, right? This one is the second curve. This one is the compression. Okay. You can review soil mechanics now, this one. Okay. I have no time to explain everything, but anyways, if you look at the question, OCR here is 1. Okay. If OCR is 1, it means that the soil is normally consolidated. Okay. It's normally consolidated. So this means the soil is normally consolidated. So this formula, we can simplify to just use CC. We don't need the recompression curve. Okay, because we're only talking about this part. Okay, for the consolidation. And then we just need the final divided by initial. So the formulas get simplified. Okay, because it happens in the compression curve. Okay, because the formula given at the back, right? Yeah, this formula. This one is the pre-compression. This one is the compression. It depends on the graph. Okay. As in, if this one tested last year, they won't test it this year. Oh, really? Oh, no, because the problem is you don't know this. It's the pre-consolidation stress. Do you remember that what that is? So imagine you compress the soil already there, then you leave it. That's the sigma P. Okay? So you consolidate it until it's overly consolidated. You remove the stress and it will go back, right? It will go back to here. But so this one is like the turning point. How much stress you need to put it back to compression, like compression stage, not recompression. Yeah. So you cannot use this like directly because you don't know sigma P. Okay. Actually, they give it. Yeah, they never give, right? Yeah. Yeah. So this one requires a little bit of soil mech knowledge. Yeah. But but after that, it's quite straightforward. Okay. So yeah, first, okay, you have layer, right? So layers. So layer 1, 2, 3, 4, right? Then you have H. H is your initial depth. Okay. So 0 0.5, 0 0.5, 1, 1. So 0 0.5, 0 0.5, 1, 1. So that's your H. Then what else do you need? You need the final and initial stress, correct? So for the initial stress, so remember, 0 usually means initial. Okay, 0 usually means initial. So sigma 0 prime is the effective stress before you add the foundation. Okay. So in this case, or not before you add the foundation, before you add the, wait, do you add the weight of the foundation? Okay, never mind. Anyways, so we find so for example, I'll just give you one example. So for layer 1, your middle of layer is located here. So what's the initial effective stress there? So you take this depth, right? So the depth is, this one is 0 0.5, you add 0 0.25. So 0 0.75 meters, right? So 0 0.75 meters multiplied by the buoyant effective weight. In this case is 18 minus 10. Yeah. Okay, then you get something like, so you get 6. Okay, then you do it for the rest lah. Okay, then you have the final effective stress, right? So this one, it basically asks, okay, imagine you now put the loading, right? How much does the stress add? So this one, they ask us to use the 2 by 1 method. Okay, so you all still remember? Is yes, is the first one. This one. Okay, yeah. So you add the loading, right? So below the foundation, at some arbitrary level, right, the stress will be added that much, P over A. Okay, and what's A? It's B plus D times L plus D. Okay, this one you need to remember. I think this one comes out quite a lot. Yeah. So it combines a few concepts like in one question is. Okay, so in this case, so sigma F prime, right, is P divided by B plus D, L plus D, right? So P in this case, you can use, oh, this one SLS, right? Settlement you use SLS. So you just need to 30 plus 110, 140. So P is 140, right? Because we're doing SLS, so we don't need to use partial factors. Yeah, that's the word. Yeah. So in this case, 140 divided by B is, oh, actually before that I'll add one more column. I think it's easier now. So I'll add D. So this one is 0.75. So D is the location of your center. Okay. So this one is D. Okay, so you can do it here also if you want. So in this case, 1.25, right? Yeah, 1.25. 1.25 and so on. Okay, but anyway, so B is 1, D is 0.75, L is 1, D is 0.75. Then you just get the change in stress. Okay. Oh, sorry, this is still the change in stress. The sigma final means this one plus this one. Okay. So sigma finals is sigma initial plus change in sigma. Okay, then you'll get the value. Okay. Then what's after that? Then you have all the information you need, right? It's a bit messy. Okay. But anyways, now you have all the information. Then you just need to plug in this formula. Correct? You plug in that formula. So you get SOED. That's your settlement. Then mu C is what? This one. Mu C is based on your area. So for your area is 1, right? So you bring it up to here. It's around 0.9-ish, 0.97 maybe. Okay. 0.97, 0.97. So your SC, you just multiply this by 0.97 and then you add everything up. Okay, any questions? This one a bit lot of concepts. Yeah. H is your depth of layer. So imagine your layer is this much, right? Then you compress it like this much. Yeah, so H is your initial depth. Yeah. Yeah. I'll show you the working here. I think it's nicer. Okay, not this one. This one. So this is your yeah. So you just refer to this, yeah. You can try by your hand yourself. Yeah. By hand, yeah. This one for NC. Yeah, I use Excel, lazy. Okay, can ya? Okay. Actually, the force here is actually questionable. Actually, is it? Depends on the question lah. Are they asking the consolidation? Like, okay, imagine the wait, is it the consolidation by the force only, or is it like when you put the foundation, then you add the force? In the solution, I think I use the weight of the foundation as well, because I assume the initial state is the foundation is not there yet. So this is the consolidation. Yeah, so it depends on what the question asks for the force. Yeah. Okay, so maybe 5 minutes break first. It's exactly 1 hour. I'm quite happy. It's exactly the questions, Suzu. Yeah. So no, I don't know about lah. Because three and four is template. 3 and 4 is template. 1 and 2 is the hard one. Yeah. I always do 3, 4, 1, 2, something like that. Yeah, can. Okay, so I'll be accepting questions first, and yeah, 5 minutes break lah. Then we continue 7:05 on there. Wait. That one is. That's where is it? Here. MV sigma. Yeah, that one, right? Yeah, Phantom's chart. Oh, yeah, Phantom chart. Phantom chart. Yeah, so that's of what? Phantom chart and this one. Yeah, two only. No lah, there's elastic settlement, CPT, SPT. One. Yeah. I think no, I think that one is the hardest one only. Because that requires you like to know the table, that requires you to know another concept. Yeah. This one I think is yeah, elastic. I think you just need to know this for elastic. It's the superposition. Yeah. So again, they do it in layers, but a bit different from the one just now. This one is superposition. I'm pretty sure it's either this one or this one, the Shirtman. Yeah, you need to draw the thing. Wait. It's legit very popular.
Yeah, I see the yeah, I see it. Cycle. Yeah. My fancy right.
Do 18, yeah, as in we do the template questions first, then we do the. No, I think yesterday's people. Oh, yesterday's. Oh. Oh, the RC, is it? No. Okay. But honestly, it's standard build the questions. It's like they don't change much like the. Oh yeah, 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 the one. Okay lah. Okay lah, we continue ya. Okay. Okay, let's start lah. Okay, so two situations where deep foundation is used instead of shallow foundation. So this one theory also. So one is when your topsoil is bad. Because if your topsoil is bad, right, it cannot carry any load. So you need to like bring it down to the strong soil. Okay, you cannot just put it in the topsoil. Second one is big load, like big load also can, then or near slope also. Because near slope, right? This one is quite dangerous. Like if your slope fails, then your foundation also fails. That's why we need to use deep foundation near slopes. Okay. Okay. So this one theory only. Okay, next. So this is the template question. That's all I can say, lah. Yeah. Anyways, for example, they give a 0.9 meters diameter. Yeah, this one, this one. They give you a two clear. Yeah. Yeah, so this one is template lah. When you see this, right? When you see piles and you see like the what's it called? The resistance, right? There are two, yeah. There's two. One is bearing capacity, two is your shaft resistance, correct? So sorry, base, yeah, base, that's the word. So you have base and also the shaft resistance. Okay. So this one I think is QB, this one is QS, I think. Okay, so upper clay is 10 meters thick. 10 meters. Oh, then bottom one is, yeah, they never give. Okay lah. Is it okay if I just use my solution? So I don't need to write. Yeah, I'll just use my solution. Okay, let me go there. Yeah, because yeah, it's nicer to present it this way lah. Okay, so when you see that question, right? First things first is draw out the soil layer. Okay, draw out the soil layer. So they just now they give you the first one is 10 meters, right? Then these are the properties. Then second layer they never give, so it means it's very deep. Okay. So these are the properties. Then they give you the loading, right? Then they give you the diameter. Then this is your pile depth. We assume that it goes into the second layer. So that's our initial guess. Okay, so our initial guess, the pile is very long, so it penetrates the second layer. Can there be a case like this? The answer is yes. Okay. So yeah, there can be a case like this. There can be a case like this. Okay, but we assume the long case first, the longer case. Okay. So they asked us to design based on DA1C2, right? So for DA1C2, if you remember, there's A1, there's R1, so action and resistance, right? Action, resistance. There's also M1 and M4. This one is for piles. Okay. So always use M1, yeah? Always use M1. M4 is only when, sorry. What? What? Wait, let me check the table. Let me check the table. Oh, sorry. Um, yeah, M1 is when there's no negative skin friction. If there's negative skin friction, you use M4. I think that's the. Oh, it's R4. Okay, not M4. R4. Yeah. So yeah. So for DA1C2, you use A2. There's M1 and M2, right? If you see there, right? Use M1. Yeah. Use M1. Okay. Then R4. Yeah. So A2 plus M1 plus R4 for general design resistance. Okay. A1, A2 plus M2 plus R4 unfavorable design resistance. So you can write down. So it's basically negative skin friction. Negative skin friction is unfavorable. So if there's negative skin friction, you use M2. Okay, but usually they will only test M1. Okay. So A2, M1, R4. Okay, these three. And there's also R4 star. That's only when there's a verification of SLS. Okay. So if they give you that line, then you can use R4 star. Okay. Yeah, but anyways, they give you this information, right? Then from here, then you start calculating the base resistance and the shear what? Skin friction. Oh my god. Okay, that's the word. Okay. Okay. So first things first, we do the load first. Okay. Okay. Wait. Okay. Okay, we need action and resistance, right? Action and resistance. So wait, let me check the back first. Um, end bearing and shaft resistance, right? Okay. So end bearing and shaft resistance. Okay, remember these two, end bearing and shaft resistance. So we know the area of the pile. We have there NC, CU, and sigma Q. So AP and NC, I think it's pretty straightforward. AP is the area of the pile, the base of the pile, right? Then NC is the bearing capacity. Yeah, is this. Yeah. Then CU, then sigma Q. Okay. So CU, you know CU, right? Then sigma Q is similar to the sigma Q is the total stress at the bottom. Okay, so it's similar to the shallow foundation just now. Okay, so you need to find the sigma Q here, and just plug in everything. Okay, so that's the logic. Then for MC, now we have this factor. Okay, D over B. Okay, so in this case, we usually assume that MC is 9. Okay, we assume that D is very big. Okay, very big. So if D is very big, D means the depth of the foundation, right? So if your D is very big, it means NC will most likely be above 9. That's why we just limit to 9 directly. Okay, so our first assumption is to set NC as 9. Okay. D in this case is this one. This one is D. Okay. Why is it D? Why is not this one, right? This one is not D. D is from the second layer to the bottom. It's because you need to refer to the cases. Where is it? Yeah. So for undrained pile resistance, right, base resistance, if it's only one soil layer, your D is the pile length. Okay, but if there are two layers, your D is just from the second top of the second layer to the pile bottom. Okay, so that's D. Okay. But anyways, we're assuming MC equals 9, so it doesn't really matter for now. Okay. Then from there, so QD is again, this one is your area of pile. This one is your Q plus, what is it? What's the formula again? APMCCU. Okay. Oh, sorry, this is loading. Sorry, this is not. Oh yeah, what am I thinking? Okay. Sorry, this one we're doing from action first. Okay, these are the actions, yeah. These are the actions. So for DA1C2, it's 1.0 GK, 1.3 QK. 1000 is given in the question. Where is it? 1000. Then they give you 200 is the variable. So QK is 200. Then this is your width of foundation, width of pile. So we don't know the length. Okay, that's why you have LP here. Okay, so that's our actions. Now we go to resistances. So resistance, again, we need to find sigma Q. So sigma Q is the stress at this level. At this level, right? Okay, total stress. So it's 18 times 10, 20 times LP minus 10. Okay, so that's the reasoning. So we get this in terms of LP. Okay, and then it is the one that we state just now. We assume that pile length is very deep. So D is very, very big. Okay, so means D, okay, it's like this. Okay, so NC equals 9. And this one is your formula. So just now is QB is your AP times NC CU plus sigma Q. Okay, so you just follow the formula. You check what you need in the formula. Something to take note is, where is it? CU. For the CU, again, we're using the CU of the base. So we are using 150. Okay, we're using 150. Okay. And then you need to divide by this factor. This one I forgot what it's called, but you need to divide by it. So this one is your 1.5. Sorry? Oh, model factor. Correct. This one is the model factor. Yeah, so 1.55. Okay. Actually, this question will always come up. So I'm just covering like just the steps, but you want to brute force it is okay. Yeah, anyways. Okay. So and bearing quite straightforward, yeah. This one is like your shallow foundation. Okay. Any questions? Anybody confused? Um, this QD. Okay, so the idea is just to get the shallow foundation formula. Is the AP times NCCU plus sigma Q. Okay, then you just like find each one. So sigma Q is here, and yeah. Okay. Next one is your shock resistance. So shock resistance is a bit different from bearing resistance, the one that we did just now. So imagine this is your pile, right? This is your pile. So shock resistance is your resistance along the like perimeter. So imagine you have a cylinder, right? You have a cylinder. So the shaft resistance is the friction around it. Okay, is the friction around. Okay. So if you look back here, it's your pile, right? Okay. So the friction comes from two parts. There's the first layer is the friction by the first clay. Then you have the second layer, friction by the second clay. Okay. That's why we have two cases. And we will add up, of course. So we do the first clay first. Okay. So the shear stress along the pile, right, is what we call the tau interface. So this one means interface, yeah? This one means shear stress. Okay, so it's the shear stress of the interface. Okay, you can see it in the formula sheet, I think. Here. So this one is your interface shear stress. Interface shear stress. Yeah, you just need to follow these, yeah. So we follow the non-displacement paths. Okay. Okay, some people ask, like, what's the difference between displacement and non-displacement? Okay, so I'll explain first. So for displacement piles, these one are usually the driven piles. The logic being, imagine this is your soil, like soil, right? What you do with driven piles, right, is you have a big block of concrete, then you just like shove it in, yeah, stuff it in there. Okay, so that's what driven piles is, okay? That's why it's called displacement piles, because it displaces the soil. Okay, because we just you imagine that, yeah, like you have a cake, then you have like a stick that you just, yeah. Yeah. Oh yeah, okay. Oh yeah, I didn't mean that. Sorry, guys. Okay, but anyways, for non-displacement, this one is your board pile. Okay, board piles. So what this means, right? You have your soil. You drill a hole first. Okay, you drill a hole first. Then you put concrete inside. So that's what a board pile is. So you dig the thing first. Okay, so you don't displace the soil. That's why it's a non-displacement pile. Yeah, so that's the, can you imagine, right? Yeah. So one, you just stuff it in there. The other one, you drill a hole first. That's why one is displacement, one is non-displacement. And if you see the question just now, they specifically state is a board pile, I think. Where is it? Board concrete pile. So it's a non-displacement pile. Okay. So if it's a non-displacement pile, okay, so it's an undrained non-displacement pile, right? Undrained non-displacement. So you follow these. So you check the CU, you plug in the formula. Okay, then alpha is just alpha CU. Okay. But anyways, yeah. So check the CU, find the alpha, find the stress, shear stress. Okay, then remember, right? Force is just stress times area. The one that we've been finding is the shear stress. So we need to find the area, right? But this one is not the base area. That's the difference, huh? The area is the, what's this called? The sleeve. Yeah, surface area is the sleeve of the pile. Okay, because the friction comes from the perimeter, right? So you multiply by pi times d, so 2 pi r. This one is 2 pi r also. It's not pi r squared, it's 2 pi r. It's the sleeve area. Okay, so sleeve area. Okay, so this is your shear stress on the interface of the first clay. This is your shear stress of the interface of the second plate. This is the 2 pi r, 2 pi r. And times the length, Because we have the whole length of the pile, right? Yeah. Yeah, so yeah, then you divide by the model factor. You always divide by the model factor, by the way. This one is your because soil is unpredictable, right? That's why they always divide by this model factor. Yeah, that's the reasoning. Yeah. Then from there, yeah, this one is your this one means resistance is bigger than your action. Okay, so your action is QD. Your resistance you need to divide by a partial factor again. The one just now is your model factor. Now it's a partial factor. So you divide twice. Okay, so first time you divide by model factor. Second one you divide by the partial factor. Okay, then you just solve for solve for LP. Okay, anybody confused? You can slowly read through. I'm just explaining the logic only. Okay, so there's always two parts: bearing and shaft resistance. Yeah, yeah. Especially the area. I think the area. I think most people get confused. How to draw? This area. Okay, yeah. Okay. You want me to zoom? Okay. Okay, itu dah. Any question? 50.14. Yeah, this is a top solve. Yeah, because they have different CU, right? Yeah, so their shear resistance also different. Yeah, that's why we do one and two. Actually, if your LP, okay, LP is 27.5, right? Our assumption is LP extends below 10. So we always need to cross check. So if your LP is somewhere here, then actually you need to redo. Actually, but it rarely happens. Usually the pile is very deep. Yeah, so yeah, yeah. Okay, so bigger than 10. No time, if you really no time actually. Yeah. Yeah, just say check field. Yeah. Okay, so yeah, the next one is what's the purpose of the pile load test and what is a trial pile, right? So pile load test, imagine you want to build a foundation, right? Then it's like probability, like just take some sample, right? Yeah. So you test some of the piles, okay, just to check whether it's okay or not. Then what is a trial pile? Basically the pile you test, yeah. Yeah, sacrifice. Yeah, correct. So your pile load test is to verify your installed pile's load capacity. Yeah. So again, it's like probability, right? So you just take some. Then trial piles is there are two types of piles that you test. So one is the working pile, the other one is the trial pile. Yeah. So working pile is actually the pile that you will use in the final building. Okay, so you don't want to load it too much. At 150%, correct. Well, this one you load it for 200, I think 200%. Yeah, because it's meant to breathe. Yeah, basically. Okay. Yeah. Okay, can I? Okay, then question 4, this one for 22 and 23, this is like the special case, like you can see. It's usually they ask for like gravity walls or embedded walls. This one they ask for I don't know what the heck is this. But it's fine lah. But anyways, yeah. Okay. But the concept is the same lah. It's just find the local, sorry, the active and the passive pressure you can already. Yeah, that's the key lah. So they give you a tank, 6 by 6 by 0.4. Then water level fluctuates with the tide with no time lag. Then they give you all the characteristic values lah. Okay, this one also I won't do it one by one. I'll just explain my thought process when I see this, I guess. Yeah. So where is it? Wall friction is 0. Okay, never mind. ULS for sliding failure of the water tank based on DA1 C2. Okay, so for sliding failure, okay, so, let's see what we have here. So first we have the surcharge. So we have a rectangle here. Then we have a sand. So the distribution will look something like this. Hey, yo, wait. So that's sand. Okay, so this Q times Ka. This one is gamma prime Z Ka. You all know what Ka means, right? It's the active pressure coefficient. It's your ratio between vertical stress to horizontal stress. So you find the vertical stress, you multiply by the K value, then you get the horizontal stress. Okay. This one I think in the second session I mentioned. Yeah. Then here we have the water level, right? So we have water level. So maybe we can do this. Oh wait. Okay, let's do assumption first. So assumption 1, water level is at ground. So if your water at ground, it means the water will be like this, right? Then this one is gamma prime. Then you have water, right? Yeah. So water, we don't need Ka. Remember, water we don't need Ka. Okay, so this one is gamma water times Z. Okay, Ke only applies for, so well, this one also gamma water times Z. So yeah, that's it lah. So we have these forces. Okay. And then if you use the what is it? Same source principle, yeah, same source principle. This water can cancel, right? So actually, all in all, you only have two forces. Okay, so you have F1, F2. Okay, one more actually is the weight. Cycle. But anyways, this one, what weight. Okay, so okay, now here's the logic. You're checking for sliding, right? So sliding, you want more weight or less weight? As in, you want to check for less weight or more weight? You want to check for less weight. Okay, because if you have more weight, you can imagine the friction at the bottom is higher, right? So we check for less weight. So we want the tank to be empty. So the tank will always be empty, both in case 1 and case 2. Okay, so we want tank empty. Okay, always. Okay, because we want the most critical case, right? So that's why the tank is empty. So the weight is just from the concrete. Okay. So we have three forces. if you see my solution, I think I included the water just to show. Yeah. Yeah. But yeah, anyways, so this is your first case. So you just need to find the forces, find the moments. Sorry, not the moments. Sliding just the forces. So for assumption 2, you have your wall. So we have, again, we have the sand. Okay. So we have water, right? So the water level is now below. Then what else do you have? You have the sand, right? Sand is, so the distribution of sand. Oh wait, we have Q first. Q first. So this QKA as usual plus the sand y'all know why the distribution is like this, right? By the way, this one is the sand. Okay, why? Because this one is 0, right? It starts at 0. Here it's gamma times Z. Why is gamma? Because it's dry. Okay. Yeah. Yeah. So only below this line is saturated, right? So this one we use gamma prime Z. Okay. Then we have water. Okay. There, right? Okay. So we have a few forces. This one we can assume to cancel. So all in all, we have F1, F2, F3, F4, and W. Okay. So again, we cannot know which one is more critical, right? Because yeah, we don't know this like this area basically. Okay. Yeah, that's why we don't know which one is more critical. That's why we have two cases. Okay, high tide or low tide. Understand, huh? Okay. Yeah, it will take a lot of time, huh? Okay. Then yeah, so for overturning, the logic is the same. The difference is you just need to find the moments. Okay, but the pressure distribution is the same. Okay. Yeah. So you take the moment about this point because that's where the wall tips. Okay. Yeah, because the wall will tip something. Yeah, imagine someone pushing it now, basically. It will tilt like that. So this is your center of rotation. So take moment about this point. Okay. This one, you just follow my solution as a guide. Yeah. Lastly, this one. Now they give the wall friction. And will this have an increase in over-design factor for sliding and overturning? So this one, the answer is, of course, yes. Well, but yes for sliding. Okay. So sliding, yes. Overturning, same. No change, no change. The logic saying is, remember that the bottom of the bottom of the wall, right? There's a, sorry, this one is what? Wall brick friction between sand fill and the tank. Oh, sorry. Oh, sorry, it's here. Wait, what? Wait, what? Let me check sand fill and the tank. Oh, oh, okay, okay. I see, I see, I see. Sorry. So for sand fill and the tank, right? Oh, I misread. Sorry. This one, wall friction between sand fill and the tank. It means your resultant force will be like this. This one 17 degrees. Yeah, I misread. Okay. So in that case, you have an extra vertical force, right? Because it's the resultant force is now tilted by 17 degrees. So there's an extra vertical force. So this will both help sliding and overturn. Yeah, increase the ODF increase. Okay, because if you have an extra vertical force, imagine you want to overturn the thing, right? Yeah, the vertical force will help it push back. That's the logic. Then for sliding, if you press it harder, right, then it will be harder to slide also. Okay. Actually, wait, it's clear. It's clear. Oh, no, no, I said like the bottom is clear. So the vertical force does it help? Never mind. Sing in the clay. So okay, the bottom resistance for this one is like what CUB times B, right? Plus this one 10 delta SB lah. I think it's this one. I forgot. Never mind. Yeah. But you get the idea. Yeah. So any questions so far? Yeah, so I'm not going to I'm not going to do like the full working lah. Okay. So any request on what question you want me to cover? Maybe the settlement lah. Yeah. Let me wait. So for the updated questions, so for the uploaded answers to CV3013, you can include, but it will cancel by right there. Yeah. Wait, let me. Wait, 2021. Oh, this one. Control print. Download. Okay. Let me see. Okay, give me a second. Okay. The okay. Invalid format. Wait, give me a second. Oh, yo. Wait. Okay. Let me figure out how to download again. This one doesn't work again. Yeah, Control P. But I think the file name. Yeah. This one, right? Yeah. Control P. Yeah, right. Give me a second. Okay. Oh, okay. Yeah, so you have any specific questions? Honestly, I have nothing else to say. I won't question this. Yeah, okay. Yeah, because it's you have like a lot of finals right there. Understandable, but okay, just revise question 3 first. So that's all I can say. Question 3 and question 4 first. That's the easier one. Yeah. Yeah, 3 is file design, 4 is the retaining walls. Yeah. Yeah. Yeah, are there like any
Lecture just now, lecture I found another typo just now, but I think yeah, there's another purpose. Yes, how resistant how resistance is based on
file resistance? Both. Both.
yeah. So it's added. There was
Yeah, added the way just now. You add the divide by yeah. Yeah, I know.
more at the base.
Thanks for coming.
You see, it's how resistant, but then it's subscript B. So is it?
Oh, that's base. Base.
Oh, it's base.
That's base. Yeah.
Oh my God.
No, because it's a heading for a few slides.
Oh yeah.
Yeah.
So I think B is base, right? I think.
S is sharp. Yeah, correct. Okay. Yeah, why not? Guys, it's still recording, right? Yeah, why not? Might as well just do the thing, yeah. It's the shipment, It's the
shipment.
shipment.
I don't know shipment. I only know Berlin and rubbish.
Wait, which question is it again? 2020, 2021.
I think sometimes
Sometimes broken.
it will be open because when you print the PDF, it might take a while. Yeah.
Oh.
But I don't think it will take this while. This long.
Then never mind. I'll just use the then. Yeah, but this one is. Oh, this one. Yeah, this one. Yeah, this one edited already. Yeah. Okay. Okay. Well, some people have, but anyway. This one. 2021, right? Okay. Bearing capacity, okay, bearing capacity, okay, right? Yeah, so it's just this one, right? Yeah. The way he did it is a bit different from. I think the solution is a bit. It's fine, like it's a good guide, but that is different from what I remember. That's all I can say. Wait, where is it? Wait, wait, Hey, give a second, Okay. Okay, let's do this. Okay, let's do this. Okay. So Sherman, right? There. Okay. Let me see what they give you. They give you this, right? Okay, I'll explain how to use this. Based on what I remember, because what I remember is a bit different. Okay, so so usually they will give you okay, the question is like that, right? So you have foundation, you have the QC, then you have that shipment thing. Okay. Okay, so first things first, we need to quote unquote like superimpose this graph, like the shipment to the foundation. Yeah. So yeah. Okay. So you have this, right? So shipment, right? Remember that the zero in the okay. Let me let me switch. There. So usually the zero here, right, is the foundation level. Okay? It's not the ground level, it's the foundation level. So be careful. So the zero of a Sherman method, it starts from the foundation level, then goes down like this. Okay. Okay, that's the first thing that you need to do for shipment. Second one is you see there's that one, right? There are three stress values there, and there's also the IZP, something. Uh wait, this is a square footing, is it? Let me see. Spread footing. Oh, this one, 800 by 800. Yeah, this one. So this one is a square, right? Square footing. So L over B equals 1. So you follow to that one. What is it? L over B divided by 1. You follow the solid line. Okay, so solid line. So it starts from 0.1. So it starts from 0.1. Okay. Then we see the IZP. Oh, sorry, not IZP. ZFP first. ZFP is the Z is the depth, F is the foundation, I think P is the peak. So it happens at B over 2. So B over 2 is 0.8 divided by 2, that's 0.4 meters. And the bottom one is 2B, right? Wait, I'll write it down properly. So first you need to find ZFP. So ZFP is B over 2. So in this case, ZFPB is 0.8 divided by 2, that's 0.4. Then ZFO, F0. So this is the depth of influence. So this one is 2B, yeah, 2B. So 0.8 times 2. So that's 1.6. Okay. So let's plot it first. Remember, 0.4 is from the foundation depth. Remember, yeah? So 0.4 plus 0.5, that's around 0.9. Around there. All right, okay, 0.4. Okay, then 1.6 plus 0.5, that's around 2.1. So it's from there. Okay. Okay. you don't need to like actually draw the foundation, but I like it that way. Okay, so now we have that, right? Next one is we need to find the IZP. IZP is the influence factor, if I'm not wrong. So IZP is 0.5 plus something. So now IZP, if you see the formula, is 0.5 plus 0.5 plus 0.1 Qn divided by sigma p prime 0.5. Okay, so again, you need to know the definitions. Okay, so you have Qn, you have sigma p prime. So what is this? So you go to the Sherman, where is it? Ah, okay, remember, so square footing, we follow this line. So what this means, right? Qn means the stress at the foundation level, because this corresponds to the foundation level. Okay, it corresponds like this. Sigma p prime means the effective stress at the peak. Okay, so basically the effective stress at ZFP. Yeah, this one, ignore this. This one is just telling that it's for the other one. Okay, solid, right? This one for this. This one is for this. Yeah, this one is for the other one. Okay. So again, that's why you need to know the definitions first. Yeah. Qn, I think, is the net foundation. Can you check? I forget if Qn is the net or is it the net bearing pressure, right? So total stress or effective stress? That's the thing. I forgot, is it total stress or effective stress? Okay, so Qn. Okay, so this is Qn, right? So it's 0.5 times. Hey, wait. Let me check. So Qn is P plus W divided by A, right? Wow. Minus effective. Yeah, that's what I'm wondering if it's wait, let me see. Give me a second to look at the book first. Wow, this one. Yeah, because this one. Oh, thanks. Qn as well.
I think it's it says then
Let me see.
I'm not sure you just scroll out.
Oh, thanks.
However you need it.
Let me see. Qn.
At the bottom is all the
Net pressure on the foundation. Oh, it's a net pressure on the foundation. Okay. So Qn is the net pressure on foundation. Okay, thanks. So it's the loading by the foundation minus the soil. So it's the net bearing pressure. Yeah, net bearing pressure. So it's P plus W divided by A minus total stress. Yeah, so something like this. Yeah. So in this case, P is 120 plus the weight of the foundation, which is, what's the weight? Let me see. So weight is 23.5 times 0.8 times 0.8 times 0.5. What's that? We get 7.52 kilonewtons. So 7.52 divided by area, which is 0.8 times 0.8 minus Um, what's gamma? Gamma is given as 16. Gamma sun is 16. Okay. Gamma is 16. So minus 16 times 0.5. Okay, so this one is the net bearing pressure. Check the cheat sheet as well. Where is it? This yeah, mana? Yeah, this one. P plus WF divided by A. This one. This one is QN. Yeah, that's QN. So basically saying, if you have a foundation, you have a soil layer, there's a pressure from above, right? There's a pressure from above like this, but there's also from the side, there's also the pressure of the soil pushing back. Okay, that's why it's P plus W divided by A, but there's also the soil from the side, right? So this is gamma Z0. It's pushing back. That's why we minus that. That's a net bearing pressure. Am I making sense? Yeah, so that's the weight of the foundation plus the load. Then there's the weight of the soil around the foundation. Okay, can see. Yeah, okay, true. So in this case, Qn is, what was this? $191. Okay, that's Qn. Then sigma, I'll just draw first. So it's like this, right? Yeah. This one is your Sherman. Yeah. Then, yeah. So we're finding here, right? We're finding the stress here. So here, the sigma z is, so sigma, the effective stress. We're finding effective stress at the peak. So effective stress at the peak means, um, what's the ground? Oh, groundwater is here. So 16 minus 10 times 1.9. You get why 16 minus 10 times 1.9, right? We're finding the effective stress at this level. Okay. So 6 times 1.9, that's 11.4. Okay. So now if you plug in the formula, you'll get, my working a bit messy here, but I didn't expect this to come up here. Oh. Yo, this. But anyways, okay, so 191.25 divided by what, 11.4, then square root. Then you will get 0.91 around there. So the peak IZP will be 0.91. Okay. Okay. So the graph will look like this. So 0.1, 0.91. Okay, that's how you construct the graph. Confused? So first things first, you check the ZFP and ZFO first. That's always the first step. Okay. So use the Sherman chart, right? Then you define ZFP and ZFO. Then you draw the line first. Okay. Yeah, so you just need to find IZP actually. Yeah, you need to find IZ. Yeah, IZP is this formula. You need the Qn and the sigma p prime. Yeah, that's IZP. Then after you find IZP, it's quite straightforward. So yeah, just connect the line. So what's the next step, right? Yeah, this one is the different from the tutorial solution a bit, how I understand it before. But anyways, how do you decide the layers for this, right? It's based on the QC. So if the QC changes a lot, it means it's another new layer. So in this case, we have two layers. First layer, second layer. So that's the difference from those PYP solution. Someone asked us, yeah. He divided even more specific. So yeah, but usually the one that how I understand it is like this. So when QC changes, then it's a new layer. And if you see the depth of influence, right, you need to check also. It means uh layer 2 only have like a portion only. It's like that much. Okay, so now what's next? Estimate the settlement of the footing immediately and 3 years after excavation. Yeah, so you need to find the settlement, right? So you need C1 and C2. So this one is definition. Delta Z. Oh, I see. Okay. Um. Okay, no wonder they divide even more. Yeah, yeah, yeah. I think you need. Wait, let me. Okay, so C1 and C2, I think pretty straightforward, right? C2 is based on the time. C1, this one you need to find again. If you have a layer, right? You take the middle, then you find the effective stress. That's sigma Q. Okay, then plug in, you get C1. 0 to ZFO means you're summing up all the contributions from 0 to ZFO. That's the sum of 0 to ZFO. IZ, you need to refer to the line. Yeah, IZ, you refer to the line. Then this one is the layer, what's it called? The layer thickness. Yeah, that's delta Z. So in this case, delta Z, the middle of layer means yeah, somewhere there. Yeah, it doesn't make sense. Yeah. Okay. Hmm, I think- So it only affects which one? It only affects. Okay, Qn is constant. This one changes. Iz also changes. Okay, wait then. Can I refer to how do you do it? Yeah. I'm not really sure how they divided the layers. Yeah. Let me check. Uh, sure. Uh, thickness 5 feet. Okay. Sorry, this one I think I need to review also. Like I forgot how to divide the soil layers. That's all. Yeah. Yeah, it's by similar values in the tutorial. I remember it's that way. Yeah, they have like one by one, right? Yeah. Yeah, yeah, yeah. That's why I'm not really sure how they divided the areas. Hmm. Oh, sorry, yeah. By the way, this one is foundation. Effective stress at foundation. This one is constant. So it only change the IZE and delta Z. Oh, yo. I think you can divide it to 3 layers actually. But I don't know if this is correct. But because the first section there's like one line, right? So you can take like maybe this as the first layer, this one second, then the last one is this one. Finish the third layer. Then you take the middle. So middle, and middle. Yeah. You can try 3 layers there. Hmm. I think okay, never mind lah. This one I think I can try very quickly actually in the Excel sheet. I'll try first. Yeah, then I'll let you know if we can divide it in 3 layers also. Yeah, because I know it's usually like one per data, right? Yeah, yeah, similar to values of QC. That's why I thought it's like a straight line. That's why I was like, yeah. Mm, how's it? Hmm. Oh, yeah. Please. This one, right? Yeah. That 3 to 4. Oh, yeah. Yeah, I think 3 days is okay because we are just finding the similar similar QC values. Yeah, then the first layer, yeah, it's like very thick, right? Yeah, as in like
Yeah, this one is supposed to be like what you see is. It says, but then I'll split it into two because there's two lines. Right. I think maybe that's why I just split it into two layers. And this one is because you see it. Oh, yeah, you can try first. I'm not really sure, but that's how we launch it. Yeah, that's why I'll do it with the answer.
yeah. Terminate at ZFO. Yeah, terminate at ZFO to determine layers. Yeah, yeah. So the problem is like, are we splitting like the first layer to two or not? That's my question. Yeah, I think just to be safe, just split the layers to two. Mm. It's quite fast also. It doesn't take much. Yeah. Um, because of cell influence factor. But they never give the. Yeah, never mind. Yeah, I think yeah, that's it. Are there like any requests? Yeah. Yeah, I said you follow the graph. So you take the middle. So let's say if this is first layer, right? You take the middle of, yeah, for Isaac. Same with layer two, you take the middle for Isaac. Okay, then I'll stop the recording, I guess. Yeah, I'll stop.